Okay, so I think we'll just get started. Hi everyone. So welcome to your second online tutorial today. So my name is Mu Yang, and I will be hosting this tutorial. So in this week's online tutorial, we will cover the hypothesis complexity and the generalization part of the lecture, and we'll also include some practical elements regarding to the logistic regression and uh, how does the theories we introduced in the lecture reflected into the actual implementations. And and finally, we'll leave some times for the QA so that if you guys have any questions regarding to anything about the course materials, just feel free to bring them up uh, at the uh, at the end of the tutorial. Okay, cool. So yeah, today we'll start by talking a little bit about the logistic regression, which is essentially a special form of the linear regression model. So we all know that a linear regression model essentially um, a linear model essentially looks something like this, right? So you have an input variable, and you have a learnable parameter associated with this input variable, and sometimes you have a intercept, and finally you have your prediction, right? So that's like a standard linear model. So if we want to use a linear regression model for classification purposes, what are some issues about this linear model? So there are a few issues. So first of all, the prediction of this linear model is unbounded, right? So it could grow really large or really small. So it's not bounded, and sometimes we want the value of the prediction to be bounded because it sometimes gives us some nicer properties, right? And the second problem is that if we are doing a classification problem, we usually want that our prediction to be reflected into probability values so that we know that just how certain is our classifier to this certain prediction. And using a naive linear model cannot achieve this. So that is the reason why we have this logistic regression model. So essentially, logistic regression models takes the original input of the a linear regression model, so which is this z value here on the x-axis, and we take these values and we apply it into a sigmoid function, which looks like this. And essentially, the sigmoid function will transform this original prediction into a fixed value range that is between 0 and 1, so that the prediction of a logistic regression model can be interpreted as the probabilities of our classification. Okay. And yeah, and the good thing is that and one intuitive question to ask is that why would we use a sigmoid function to do this? Why don't we just use like a straight line, which will give us essentially the same results, but is simpler. So the reason is that the sigmoid function is, as you can see, it's actually it's smooth, so that is second order differentiable. But for a straight line, it is only uh, first order differentiable. So that is the reason why sigmoid is better. Yeah. And later in the implementation of the codes, we'll see more examples about how to apply the logistic regression. And yeah, just to give like a more specific definition, we can express the the input of the feature we're trying to predict, which is a single x here. And we can also express the learnable weights of the logistic regression either using this combination of beta learnable parameters or this a single d-dimensional vector W, which basically represents the collection of all the beta variables here. And their multiplication plus the intercept is essentially the prediction of the linear model, which we apply the sigmoid function and will give us the result of the logistic regression. Okay, so the beta and the so the B and the beta 0 here are the same. They represent the intercept of the linear models. Okay, and yeah, to just give a recap about the concept of the hypothesis class and hypothesis. So as mentioned in the lecture, we know that a hypothesis class basically contains like all possible hypotheses or all possible combination of learnable parameters in a predefined space, right? So in the case of a logistic regression, a specific combination of the learnable weights could be viewed as a specific hypothesis, and the hypothesis and the predefined hypothesis class for the logistic regression can be viewed as this collection of all the possible parameters from the parametric space. And in our case, the parametric space it contains all the real numbers. So we have infinitely many possible hypotheses in this predefined hypothesis class, right? So that's what has been taught in the lecture. Right, and so after the logistic regression, we are going to have a quick look about the pack learning. So let's first recall the motivation of the pack learning, right? So in realities, we know that we want to sort of build a prediction models, right? And the sort of the core or the fundamental question in this process is that how do we make sure that the model we learned on the training data, the model that minimizes the training loss can be applied to the data we haven't seen yet, right? So this is called the generalization. The performance of the hypothesis on the data we haven't seen yet is called the generalization of this hypothesis. And pack learning basically tells us is there a way for us to estimate or to measure, or is there a theory to guide us to about how should we estimate the generalization or understanding the generalization of the learning algorithms, right? Okay. Yeah. So recall the motivation of the pack learning. So the pack learning is called the probably approximately correct learning, right? So the reason we have this sort of a degree of freedom in our statements, such as probably and approximately, is because the data generation process in reality could be sort of random, right? So there is no deterministic rules for the generation of the data in reality, like sometimes, right? So in this case, you could practically you could never have like a model that can give 100% accurate predictions, based from a somewhat random data generation process, right? So that is why we want to have, we only want to give a statement about how probable is our learning algorithm to be correct, like given an error margin, right? So that is the reason why we have the pack learning. It is used to sort of provide this sort of a degree of freedom in our statements when we are stating like how correct our learning algorithms is, right? So as we mentioned, there are two important factors in the pack learning framework, which is delta. This corresponds to how correct, how probable is our pack learning statement, and this epsilon here corresponds to how accurate is our learning algorithms, right? So very naturally, there are two sort of abstract variables which we usually do not give like a specific values to them, but we have to sort of understand the interplay between these two variables. So if you recall the generalization error bounds we presented in the lecture, which will restate here. So this is the generalization error bound of the VC dimension, right? So we know that this guy here is epsilon, which is sort of telling us how our prediction error looks like. And this guy here is a delta, which tells us like how probable is our what is the probability of this event happening. So how probable is our algorithms to be approximately correct. And this delta here essentially depends on the values of epsilon, which means if you are saying that your algorithm is more accurate, then you can only see this with lesser confidence, because if you are increasing the level of accuracy, there will be a larger chance that you will not achieve this sort of accuracy, right? That is the probable and approximate in the pack learning. And yeah, so and what other factors usually influences the results of the pack learning? So we know that both epsilon and delta are dependent on your sample size. So essentially, this means if you are increasing the number of training data, there will your learning algorithms will be more accurate, and you can say with a larger confidence that your learning algorithms is more accurate. Yeah. And here is the definition of the pack learning. So this is sort of a restatement of the definition that has been defined in the lecture. So yeah, always refer to the definition in the lecture as the sort of a ground truth definition. Okay. Yeah, and that's it for the general framework of the pack learning. So we know that the pack learning is only like a framework, and there is like very specific sub problems in these frameworks, right? So like one of the most important problems we mentioned in the lecture is how do we check the pack learnability of a given hypothesis class, right? So we spent quite a lot of the time in the lecture to talk about how should we prove that a hypothesis class of a finite hypothesis. So in this hypothesis class, we only have a finite hypothesis. How this hypothesis class is pack learnable, right? So we have given like a quite detailed proof in the lecture, and which basically establishes that for any hypothesis class, or for most of the hypothesis class that is have finite number of hypotheses, we can see that it is pack learnable, right? But for the hypothesis class that contains infinitely many hypotheses, which is usually like a more realistic scenarios in the applications. So how should we determine whether this hypothesis class is pack learnable? So we cannot do this in a very straightforward manner. We have to choose an appropriate hypothesis complexity measure, such as VC dimension. So in the lecture, we have proved that using the VC dimension, we can sort of prove that a hypothesis class that contains infinitely many hypotheses is indeed pack learnable. So here we'll just sort of go through some of the important concepts of the VC dimension. Okay. So I think I saw there are some questions in the chat. So we'll just do the QA like together in by the end of the session, if that's all right. Okay, because otherwise we will keep stopping and sort of yeah, that's probably going to take too long to go through all the materials. Okay. Yeah. Okay. So Yeah, so basically, what is VC dimension? So as we have already defined in the lecture, the VC dimension of a hypothesis class is the largest number of points that can be shattered by the hypothesis class, right? So, so basically, defining the VC dimension requires the definition of the shattering, right? And to define the shattering, it requires the definition of Groots function. So let's start by talking about the Groots function. So the Groots function measures like the maximum number of distinct labeling of a predefined hypothesis class on m data points. Okay, so basically this means if you have like maybe 1, 2, 3 data points, the Groots function will tell about and for a given hypothesis class, the Groots function of this hypothesis class will tell you how many the number of ways that this hypothesis class can find the distinct labeling for these m data points, right? So we have quite detailed examples in the lecture, and here is again is a definition of the Groots function, and later we will see like a quite practical examples of the Groots function and how do we calculate this or how do we estimate this in reality. And once we know the Groots function, we can now give the definition of the shattering. So shattering is sort of a binary outcome operator, right? So for a shattering, there's only two consequences. You can either shatter a given set of points, or you cannot shatter this given set of points, right? So if you can shatter this given set of points, it means you can find all the possible ways to make the distinct classifications on these m data points. So how do we calculate like the maximum possible number of ways to make distinct classifications? So we know that if we have like a binary prediction problem, which means the cardinality of our label would be 2. And we have, sorry, that's quite ugly too. Okay. Yeah, so which means the base will be 2. And if we have maybe like 3 data points, these are sort of random data points, then there is 2 to the power of 3 number of ways to make the distinct classifications, right? And if our Groots function of the hypothesis class at for a point of 3 data points is exactly 8, then this means our hypothesis class can shatter these m data points, right? But suppose that our hypothesis class can only realize this or can only find 7 different ways to make the classification. It means the maximum number of ways is greater than the number of ways for classification realized by this hypothesis class. Then this means our hypothesis class cannot shatter a set of points, 3 data points, right? So if it cannot shatter 3 data points, it means its VC dimension is 2. So supposing that it can shatter a set of data points that is the set of 2, right? Yeah, so that is the definition of the VC dimension. And as presented in the lecture, we know that using the VC dimension, we can sort of obtain this associated generalization error bounds that is, depends on the VC dimension of the hypothesis class. One thing we should sort of highlight here is that the VC dimension is a so-called distribution-free measure of the hypothesis complexity. So even though that it takes like certain data points to calculate, but because those data points are in fact random data points, so that they are not actual training data of your data set, so that it is actually what we call distribution free measure, which means you don't need any data to or any actual data to estimate the VC dimension. Yeah. So that's just like a fun fact. Okay, so I think we can start by looking at some coding examples. I think this should be a good time, a good time to start it. So we can sort of while we are looking at this coding examples, we can think about some questions in the meantime. So these are some sort of like exercises or the questions that you can sort of try to work them out by yourself. So the first question is that, can you actually estimate the VC dimension of a hypothesis class? And how many steps does it take, right? And can you efficiently estimate the number of VC dimension if the number of data points scaled? So if the number of data points increases, right? So to answer these questions, we'll look at the actual implementations. So can everyone now see the VS Code here? I think so, right? Okay. Right. So the first problem is that, can you actually estimate the VC dimension? So the question is yes. Okay. So for a very toy example, we can sort of try to estimate the number of VC dimension. And here are the following procedures. So as we know that to estimate the VC dimension, we need to know that for a given size of the data points. So as you can see, we have sort of a sequence of different sizes of the data points. So we have 2, 3, 4, 5. It represents the size of the data points. So for a given size of the data points, we need to know that whether a predefined hypothesis class can shatter these data points. Yeah. So one step would be, we want to define a function that can perform the shattering. And as we just saw in the worksheets, in order to determine whether we can shatter this set of data points, we need to know what is the Groots function of this predefined hypothesis class on this set of data points, right? So if we know the number, the Groots function of if we know the Groots function of the hypothesis class on these data points, and we can directly calculate like the total possible number of ways to make unique classifications, right? And then we can sort of directly determine whether this set of points is shattered by a predefined hypothesis class, right? So that's doesn't sound too hard. We can give a try. So basically, we start by looping every single possible size of the sets. So we'll start by the smallest value. So it only have 2 data points. So we know that probably most hypothesis class can shatter these data points, right? And we will end till when there is 5 data points. Okay. So we first define the empirical Groots function, which is defined here. So basically, what this does is that we will keep trying to generate the number of ways to arrange our data points. So because one very important factor is about the Groots function, if I forgot to highlight, it's a maximum operator here. So what does this operator means? It means we are trying to find a way to arrange our data points so that it can maximize the Groots function. So we are not just arranging the data points randomly, but we are considering like a worst case scenario that it can give us the maximum value of the Groots function. Yeah, so that is the reason why we cannot actually have a exact computation of the VC dimension, because we cannot enumerate all the possible ways to arrange the data points. But we can set a really large number of trials which give us like maybe like if we have 1,000 trials, we will see 1,000 different ways to arrange these data points. And for every arrangement, we will check if this given data, this set of given data points can be shattered. Okay. So this is the first step, right? So we are trying to make the random placements of the data points based on a given sets. And knowing these data points, now we can check if they can be shattered. So how do we check if they can be shattered? We use the check shattering function that is defined here. So basically, in order to know if it can be shattered, we have to so when you are checking the shattering condition, you essentially have a set of like input training data. So they are like in a format of the combination of a label and input data. So if in this predefined hypothesis class, you can find a hypothesis that can fit this given input points, this means you realizes this specific ways of the classification, right? So yeah, I'll just try to state that again. So yeah, basically, yeah. So at every given set of the input data points, you are trying to determine whether this whether a specific hypothesis within your predefined hypothesis class exists, so that it can realize this specific input pattern, right? If it can, it means for this specific combination of the input, it can be shattered. So yeah, so that's how we achieve this, right? So we basically fit a logistic regression model to see if we can make correct predictions for a given input to predict its labels. And if we can, so if the accuracy is exactly 100%, it means we have realized this classification, and we will add one to our realized labelings. Okay. And we know that if we only have like one possible labels, then it is goes without saying that it can naturally be realized by all the linear models. So we will directly return +1 here. And if we have more than one labels, we'll try to fit a logistic regression model to it to predict whether we can realize this specific classification. Okay, so yeah, so we are keep running this. So we are keep repeating this process. Basically, we are trying different sort of a combination of the input points, and we are checking if it can be shattered. So if the number of classification rules being realized is equal to the is equal to the total number of possible labelings, this means for this given set of input, it can be shattered. Okay. And to run these algorithms, we can basically, yeah. So running this algorithm will pretty much give us the sort of a okay, so it just takes some time to install the packages. But basically running this chunk of code will give us the results that we expected, which is that for a predefined linear hypothesis class, it can realize all the possible ways of classification when we have 3 input points. But for input points that is larger than 3, the number of input points that's larger than 3, we cannot roll out this all the possible classifications, which means the VC dimension of the logistic regression is 3. So that is consistent with the examples we have shown in the lecture. Okay.
Maybe you can store the scale learning. Yeah, we should have sufficient time.
Okay. So, but yeah, I just think there is like probably more packages to be installed.
Yeah. No worries. Oh, the name is not.
Yeah.
Yeah.
Okay, I think maybe the students will just run the code like later on their own devices. And I will not try to run the following code because apparently the environment of this computer is not being properly set up.
Arrow, no worries. Let's check the arrow.
Yeah. Cool. Okay. Right. So that's all for the VC dimension and shattering and the Grooves function. Okay, yeah, and there's like one final question is, can you do this efficiently as the number of data points increases? So quite obvious, it's the answer is you cannot, right? Because essentially, you need to at every step you need to check that whether it's the number of classification you found is the same as the total number of classifications. So apparently the not total number of classification is cardinality of the y to the power of m, so which can grows like non-polynomially if the number of data points increases. So very obvious that the VC dimension is actually mostly a conceptual, theoretical properties of the hypothesis class that even though you can calculate for a very toy, a very small example, but when your data point scales is really impossible to calculate. Okay. Yeah. Yeah. And after the VC dimension, we will talk about the approximation and the estimation error. So yeah, so I think this figure should be you should be quite familiar with this figure, which basically it decomposes the error of a hypothesis into the estimation error and the approximation error. So so basically we know that the approximation error sort of measures how good your predefined hypothesis class is, right? So it measures the distance to the optimal hypothesis within your predefined hypothesis class to the target concept. So once again, the target concept is the underlying true is the true mechanisms for the generation of the data, right? So this is like the golden standard for how the data is generated or how the data is labeled. And we want our hypothesis to approximate this as close as possible, right? And the approximation error basically tells us how good your predefined hypothesis class is. If your predefined hypothesis class contains the target concept, this means you have like a 0 approximation error, which means you have for the specific task, you have a quite a nice predefined hypothesis class. And for the estimation error, it measures the distance between the hypothesis that minimizes the training loss and the optimal hypothesis within the predefined hypothesis class. So this measures like how good are you fitting the data. So even though you have you could have a near zero training loss within this predefined hypothesis class, but your generalization error could be probably worse, right? You could be overfitting the training data. So if it were to reflect it to this figure, it could mean that you have a relatively larger estimation error, right? And this is some sort of a more formal definition of the approximation error. It is the infimum of the distance between any arbitrary hypothesis to the target concept. So we know that the hypothesis within the predefined hypothesis class that has the smallest distance to the target concept is the optimal hypothesis, which we denote as H prime here. As the estimation error basically measures how good is your hypothesis that minimizes the training loss, so that if it is very close to the optimal hypothesis, it means you are fitting the. It means you are finding like the relatively good hypothesis within the predefined hypothesis class. And for now, we'll talk about what sort of factors influences the estimation error and the approximation error, right? So more specifically, we're going to talk about how this has to do with the hypothesis class complexity. So we know that if a hypothesis class have a larger complexity, this means we usually have a smaller approximation error. So the reason is because if we have a very complex hypothesis class, which means this H here could be larger, like in this universal function space. So there is a larger probability that it will cover the target concept, or it can generate a hypothesis that is much closer to the target concept, right? So this basically tells us why a more complex hypothesis class will usually have a lower approximation error. We cannot see this deterministically because it is not certain, but with a larger probability. But if we increase the complexity of the hypothesis class, this means we are also under the risk of increasing the estimation error of increasing the estimation error of this hypothesis class. So this is because if we are increasing the complexity, it means our hypothesis class will have more capacity to learn the sort of the random or the noisy information within the input distribution, right? So for instance, it could be like the noise on the features or the noise on the labels, or but to in summary, those information will not help you in generalization, right? So if you fit this sort of irrelevant information, it will be overfitting, and they are usually bad for the generalization. So that is the reason why increasing the level of complexity of the hypothesis class will hurt the estimation error. So there is sort of an inherent trade-off between the approximation error and the estimation error, right? So it's sort of like a bias and variance trade-off. And actually, bias and variance are very closely related to these two concepts. So there is like no silver bullets that can give you like maybe optimal approximation error or estimation error in the same time. Yeah. Here are some like general ways that we can reduce the approximation error and estimation error. So as we mentioned, in order to reduce the approximation error, we can increase the complexity of the hypothesis class, so that it is with a larger probability that it can cover the target concept, or it could be more closer to the target concept. Or we can inject more prior knowledge to this hypothesis class. So if we know that like our target concept if we know sort of the information about the target concept, then we can sort of handcraft a hypothesis class that is tailored specifically to this target concept. That is actually called inductive bias. And you can see that a lot in either modern deep learning applications or some conventional learning algorithms. And as for minimizing the estimation error, so one thing that we should highlight here is that the estimation error is actually what we want to quantify in the pack learning framework. Okay, so let's recall the pack learning framework where we are bounding the we are essentially bounding the estimation error of hypothesis in the predefined hypothesis class. Okay, and earlier we have mentioned what we can do to make the error bound of the pack learning framework more tight, right? How to tighten the generalization error bound. So to do this, the approach are the same to minimize the estimation error. Basically, we can use regularization techniques to sort of to constrain or to regularize the complexity of the hypothesis class. So what this means is that if we are applying regularizations, we are sort of like we are having this smaller or more constrained areas in this hypothesis class. So for instance, if you have like a L2 regularization, we might think that these outer areas have a larger L2 norms, and they tend to be these areas tend to be avoided during the optimizations, right? So that is one way we can apply the regularizations. And another way is that we can, as usual, we can increase the number of training data to better find the best hypothesis within the predefined hypothesis class, right? So that's for the same reason as pack learning. And one thing that probably we should highlight here is that increasing the number of the training data will not help your approximation error, because your approximation error is determined once you have choose the predefined hypothesis class. So it remains static during the process of the fitting, or during the process of the optimization, during the process of the learning. So increasing the number of data points will actually not help the approximation error. Okay, so that is probably a little bit abstract to perceive. So we will also look at some more concrete coding examples to basically which tell us how the approximation error and estimation error will looks like if we have like sufficient training data. Yeah.
So before, I think the notebook already contains the result. You can just try to use the
Yeah.
previous.
I will not to try to run it again. Yeah.
kind of
Yeah. Thanks for the heads up. Yeah. Cool. So we'll have a look at the code again. Okay. So we'll consider like a synthetic data set for these specific examples. Okay. And basically we assume that this specific this synthetic data set follows the Gaussian distribution. Okay. So we sort of know the true distribution of the data that we have here, which means we know we have knowledge to the target concept, right? So this usually does not happen in reality, but here, just for the simplicity, we will make such assumptions. Okay, so we have two Gaussian distribution associated with two groups of observations. So we know that the first groups of observations are sampled from this first Gaussian distribution, whose mean value is zero, has a zero mean, and identity covariance. Okay, so that if the diagonal of the covariance matrix is equal to 1, it means it is identity covariance. And that is the distribution of the first Gaussian distribution. And we know that this group of x1 is sampled from this distribution. And for the second distribution, its mean value becomes 2 and 2, but the covariance remains the same. And we know that the second group of the empirical observations are sampled from this distribution. And basically, we assume that for each group of the X of the feature, it has like it belongs to a specific category. So the X1 associated with label of Y1, which are zeros. So their ground truth label is zeros. Okay. And for the second group, their ground truth label is associated with the with another category, which is one. So this is sort of like the target concept, right? We have the underlying rules of the data generation. We have the underlying rules of the labeling process. So it is like if we know the target concept. And combining them together, we have the training data, which is in this case, it's quite obvious it's a linear, it follows like a linear relationship, right? You can use or in other way, you can use a linear classifier to uh to 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 uh to achieve like the optimal classification rules. Okay. And to make things harder, we will also consider a nonlinear case, which is called a XOR pattern. So the XOR pattern is like quite a classical a classical ways for generating the nonlinear data. So it is sort of like if you have data that is arranged in this way, so that you can see no linear models can make predictions for these four data points, but a nonlinear model could easily achieve this. Okay, so this nonlinear model can, so this nonlinear data set can easily be generated uh, just like using these rules, and we will basically try to visualize how these two data sets look like. So for the first data set where we have the linear, so where a linear decision rule can sort of achieve the optimal results, we can see that even though it cannot make the perfect classification, it cannot perfectly classify all the data points, but it can achieve like a reasonably good performances. And later we will show that it can achieve no better than this. So that's so you can see that like somewhere around here is like the centroid of the first Gaussian distribution, and somewhere around here is the centroid of the second Gaussian distribution. And there is some parts that they are entangled. And for the nonlinear data, it is quite obvious that it is like a XOR relationship I have just described earlier, where you cannot use a linear model to make prediction. And in fact, if you try to use a linear model to predict this, the performance will be almost like random guessing, right? Because no matter where you draw a line, there is always like somewhere around half of the data points that you'll be misclassified. That's the second data set where the optimal rule is not linear. Okay, so now we will try to fit a logistic regression model, which is obviously linear, to these two data set respectively, and we will have a look at their performances on these two data sets. And we can see that for the linear data set, our logistic regression model can achieve an accuracy that's around 92%, which is so this is actually very close to the optimal error rate that it can possibly achieve, which we'll show that later. But for the nonlinear data, that is the XOR relationship, it can only achieve performances that is somewhat similar to random guessing, right? So it only have a 51% accuracy. And if you average for more runs, it will be, I think, closer to 50%, closer to random guessing. And we can have a look at the decision boundary of the logistic regression model. So that's basically like very similar to what we have conjectured before, right? So we have so even though some data points will not be correctly classified, it is the best possible results we can have. for a linear model. But for the XOR data sets, it's also like we imagined, no matter, as long as you're using a linear model, no matter where you draw the line, you will only have a near random guessing results, because this inherently requires a nonlinear model to learn. Okay, and yeah, so that's basically related to the target concept. Okay, so we know that in the first data set, in the linear examples, that the target concept can be resolved by a linear model, or which, in other words, we can use some sort of a linear relationship to explain how the data is generated. So for a linear hypothesis class, that is a hypothesis class of the logistic regression, it is more likely that it contains the target concept, or it has a really smaller distance to the target concept. But for the second data set, where our target concept is nonlinear, so it is very obvious that no matter how we try, no matter how good is our fitting to the training data, we can never obtain a good result. That is because the approximation error of the logistic regression is too high, that that estimation error could be sort of it only accounts very smaller in this process because the approximation error is so large. Yeah. And finally, in this example, we will sort of observe how the so as a matter of fact, it is usually that we cannot so while we have mentioned that we can theoretically decompose the error of a model into the approximation error and the estimation error, but in fact, in reality, it is very hard to do so, right? Because you don't know the target concept, and you usually don't know the optimal hypothesis H prime. So it is very hard for us to determine the approximation error and the estimation error. But in this example, we will have a look like about how we can have a very coarse estimation about the how to sort of observe the behavior of the estimation error and approximation error when we are increasing the number of the data points. Okay. So here in this example, we are basically we are downsampling from the original distribution. Okay. So we have yeah, so we have this different level of a number of data points. So in the first case, we only have 10 data points from a certain distribution, which means we can only have like a very poor approximation of the distribution, right? But for the last case, we have like the relatively more abundant number of training data, which should give us a more accurate approximation of the original distribution. And we know that basically the approximation of the distribution we have talked about is related to the estimation error, but not the approximation error. So while we increasing the number of data points, which it is very naturally that we can observe like a decrease in the error of the classifier. But what we actually observe is a decrease in the estimation error, because we know that the approximation error has nothing to do with this process. So yeah, so in this example, we'll have a look like how this is going to how the logistic regression model is going to behave when we sort of set up this very tall example. Okay. So we can visualize this the test error based on different number of the training data in this figure. And it's very clear that as we imagined, as the number of data point increases, the test error will sort of asymptotically decreases as well. And we can observe that the margin, the standard deviation of the error also decreases sort of asymptotically as well. So So as we mentioned, this is actually corresponding a decrease in the estimation error. And eventually we can see that at a certain point, the performance of our model converges, and it will not further decreases. So this is yeah. So I think this is a linear example, right? So actually for this example, the error we saw here, which corresponds to this sort of a unreducible error, is not the approximation error, but the error of the target concept. Okay. So even though we know that the target concept corresponds to the best possible decision rules that you can possibly have, but it is not error-free. So in certain cases, even the optimal decision rule, even the target concept, will not give you the like the zero error in certain cases. So yeah. So we'll sort of witness this example by the distribution of our data, which we saw earlier, right? So you remember that we talked about that our data is generated from two Gaussian distribution. The first distribution is zero mean. So it's this blue distribution in the left. And the second distribution have a mean of 2. And this is a red distribution to the right. We can see that there is a quite a large area that is entangled together, which means for this very specific area, their axis will be completely indistinguishable for a linear model, right? So if you draw like a line here, yeah, that's supposed to be a straight line. And for the data points in this area, you cannot like always have a correct prediction. You cannot always have a correct prediction. Okay, so I think I saw a question that should be addressed right now. So what is the meaning of the diameter, right? So the diameter of these two distributions, they are the covariance of the Gaussian distribution. So we are having a two-dimensional Gaussian distribution, and the diameter is a covariance. If you have like you only have a one-dimensional Gaussian distribution, you will have like a standard deviation to control like how uncertain is your distribution, right? So in a one-dimensional case, it is a standard deviation, and for the two-dimensional case, for the multi-dimensional case, it is covariance. I hope this answers your question. Okay, yeah. So back to what we mentioned. So even for a target concept, it cannot know like which data, what is the ground truth label in this entangled area. Yeah, you cannot know what is a ground truth label to this entangled area, and we will actually show that in a very detailed derivations. Oh, okay, and the one thing that probably worth highlighting here is that this part is sort of optional to just for your references, because they are clearly not examinable, and we only discuss this to help you better understand the content of the course. Okay. Yeah. So basically, if we know the generation process and the labeling rule of the distribution, we know the target concept, and we can express them in this probability distribution, right? Because we know they are both Gaussian. Where is it? Yeah. So we know that. So we know the distribution of the data. We know that they are both Gaussian, and we know that the distribution of the label is balanced. We know that the prior of the y equals to 0 and the prior of y equals to 1, they are both 0.5. Okay, and now we will show how to use the base decision rule to obtain the the optimal classifier and what's its risk, what's its error rate. Okay. So we know that if we make the correct prediction, it's a correct prediction rule looks something like this. So this is because so because if the ground truth label is 1, this means our prediction should be greater to the predictions of x being 0. So this is because of the properties of the logistic regression, right? So logistic regression looks something like this. So if the ground truth prediction is if the ground truth label is 1, it means our prediction should be somewhere around this area. So it should be greater to the prediction of this area, right? So we are basically assigning labels based on our prediction. Okay. So yeah. So I think that's quite clear, right? And that's like the ground truth decision rules, right? And we can also express this by using the marginal probabilities of the x. So why do we want to use the marginal probability of the x? Because we know that the x is generated by a very specific distribution, which is Gaussian. So in order to sort of have the exact probability of the results, we will sort of need to transform this conditional probability on y to the conditional probability of x. So which is called the margin the conditional marginal distribution, I think. And because we know that the distribution of the label is balanced, so we can actually cancel off the prior here, right? Because they are both 0.5. So, and even if they are not balanced, it actually won't going to it's not going to hurt the final results because they will only serve as a constant here. Okay. So we can transform the decision rules using the marginal probabilities of x. So here we are expressing them using y, but here we're expressing them using x. And we'll show that we can, because the probability of the Gaussian distribution or the CDF of the Gaussian distribution can be directly calculated, so we can have the exact value of the decision rules. Yeah. Okay, sorry, my mistake. It's actually the PDF of the Gaussian distribution. So yeah, so we know the PDF of the Gaussian distribution, and we simply substitute the values into this decision rules, and we will obtain this sort of a complex, sort of a complicated looking formulas. But just know that because we know the distribution of the true parameters, so this very complex looking formula will essentially just be reduced to a specific value because this is something we can calculate, right? And yeah, and by substituting the values into this formula, we have the optimal decision rule. So that is, if x1 plus x2 is greater than 2, then this should be assigned. So the label should be assigned to 1, and it should be assigned to 0 otherwise. Okay. So this is, so if you just sort of rewrite this equation here, you can obtain you can obtain parameters for the linear regression model, right? Yeah, so this line basically corresponds to the linear regression model. Okay, so now that we have a very clear, explicit expression of the optimal decision rules, we can calculate the expected risk of these decision rules. So how do we do this? This is we simply resubstituting the sort of so as you recall, we mentioned that because we have two Gaussian distribution that have entangled areas which we cannot distinguish, right? So the expected risk, so this should be a straight line that divides here somewhere, yeah. So we know that the risk of the optimal decision rule is essentially the cumulative density function of this part. Yes. So when we are calculating like a portion of the distribution, we are using the cumulative distribution function. And since we know the cumulative distribution function of the Gaussian distribution, we can also directly substitute the parameters of the distribution and obtain the PDF. So this PDF simply means simply calculates the area of this overlapping region, which we go back to the worksheets. So the CDF is simply calculating the area of this overlapping region, and tells you that if we draw a random data point and this data point falls inside this region, then we will not have a correct classification by a 50% chance, right? And directly based on these results, we can calculate the expected risk in this manner. Okay, that is 7.87%. So which is we will run that up to 8%. And if no, we will just stay at maybe 7.87%. And if we look at the visualization of the test classification error, we can see that when it converges, the error it makes, it is exactly the same as the error of the optimal decision rules. So which means the logistic regression model we have trained here is essentially the same, or it performs as good as the optimal decision rule we derived theoretically. So that is a quite nice result, right? And in this case, we also need to highlight here that for this data set, it does not have an approximation error. So we have a zero approximation error because we know that the ground truth, the optimal decision rule we just saw here is essentially linear. So there is no approximation error because the target concept is within the predefined hypothesis class. And we can see that having sufficiently large training data will give us a hypothesis that almost coincides with the target concept. Okay, and we will also use this figure to sort of to link the approximation error and estimation error. Sorry, not the approximation error, but just the estimation error to the pack learning framework. So we know that for the pack learning framework, if we have more training data, then we are increasing both the probability and the approximate and the level of approximation, right? So we are reducing the epsilon and we are reducing the delta. So how this looks like? It's basically reflected in this figure. We are witnessing that the test error is reduced when we're increasing the training data. So this can be reflected as a decrease in the epsilon, in the error of the learning algorithm itself. And while we are witnessing this reducing in the uncertainty of the prediction, right? So we can see the standard deviation of the prediction is going like asymptotically tighter and tighter when we have larger training data, right? So this actually corresponds to the probableness of the pack learning framework. So because if you have more training data, we are claiming our confidence, we are claiming our performances with a larger confidence. So we are also reducing the delta. We are increasing the likelihood of the event. Okay. And I think that's all for today's materials. I saw like a few questions earlier. So if you guys are still here, feel free to bring the questions up and we will be happy to address them. Thank you. Yeah, so it doesn't have to be specifically related to this online tutorial. It could be essentially anything that you want to ask about the course. So yeah, feel free to bring them up. Oh, and by the way, the code and the worksheets will be uploaded to Canvas later as well as the recording.